Section 4.7, page 3, the final page. So we're going to end up integrating or taking the antiderivative of this function here. And we need to point out a couple things. Now remember, we're going to be taking an exponent and we're going to be adding 1 to it. Don't forget that whenever it comes to adding with fractions, we need to have like denominators. So we need to write 1 in its disguised form of matching denominator over denominator. So we can then, in our case, add the numerators over that same denominator, and that will get us 1/2. Now don't forget also that when we do a power rule antiderivative, we need to write 1 over n plus 1. Well, n plus 1 was a fraction for us. So think about it where we have the numerator divided by the denominator. The numerator divided by the denominator, where the denominator is a fraction, means we'll be changing it to multiplication of the reciprocal. And so really I just have 2 over 1. Although remember, sometimes we might actually have already had a coefficient in front. So anytime I've got something divided by a fraction, I just need to think of it as multiplying by the reciprocal, which is the existing value, times the denominator of the denominator, all over what was my numerator. But you'll see it together in a minute. Example 3. Find f using the initial conditions to solve for the constant. So basically, this is exactly what we did in the previous problem. I'm going to take this problem, but I'm going to rewrite the question the same way I would have done if I were taking a derivative, even though I'm only taking the antiderivative. So I begin by rewriting the question. So I can go ahead and just leave my coefficient of 3 here. I'm going to take the question, and because I have a variable base with an exponent, I'm going to add 1 to the exponent, and this is kind of what we did up here. And don't forget, the denominator is the existing exponent plus 1. So even though I didn't write them identically, these are the exact same piece. Well, we already said we know from above that this simplifies to 1/2, which means this simplifies to 1/2, but we said we can rewrite it as the reciprocal of the denominator times whatever was there. So I've got 6t to the 1/2 as the antiderivative, but I always need to add that plus c when I take antiderivatives. Now, one of my initial conditions was actually an f prime. I now have enough information that I could use an initial condition to find c. I have found, I'm kind of on a roll. I just found one antiderivative. I want to keep going before I get bogged down by other steps and forget what I was doing. So I'm going to take this question. I'm going to add 1 to the exponent, which you can see over here in my denominator. But since I see it as a fraction, it needs to be denominator over denominator so that I have like fractions to add the tops to get the 3/2. So I really should have had 1 over 3/2, which is to multiply by the reciprocal. I had just plus c, but I need to multiply that by my variable, and I need to add 1 more new constant at the end. So other than simplifying that 3 goes into 6 twice, so I have 2 times 2, I now have the original function that's got 2 two constants, you could argue. Now, even though f of 4 came first, if you have a derivative initial condition, always start there. So I want to use this one first, but not with the original f of x. I don't want to use it with the answer I got. I need to use it with my f prime of x, or in our case, t. So when the input is 4, I know that the answer equals 7. So I've got 4 to the 1/2, which is really the square root of 4, which is really just 2. And so 2 times 6 is 12, but I'm solving for c, so I'm going to subtract 12 to the other side, and I'm left with c equals -5. So I could put a -5 here, but really I'm now at this step. I'm going to use an initial condition of f of 4, where I have found that c was -5, and I'm going to be solving for d. So I've put 4 in for the input, and I've set the function, or in my case, my original function, equal to 20. So 4 to the 3/2 power is really to take the square root of 4, which is 2, and then cube of 2, which is 8. And so 4 times 8 is 32. This was minus 20. So this simplifies to a positive 12, but I'm adding it to the other side so that I get d equals 20 minus 12 is 8. And now I can come put an 8 in the function. I was asked to find the original f, and I did using initial conditions to find my constraint. Here's where all of this comes into play in real life. Example 4. A car is traveling at 65 miles per hour when the brakes are fully applied, producing a constant deceleration of 22 feet per square second. What is the distance traveled before the car comes to a stop? Now, here's the things to remember. We usually start with a function that tells us the position of a vehicle in our case, or, the speed. And then when we take the derivative, that's telling us at what rate it's changing, its velocity, how it's moving forward or backwards in some cases. And the derivative of a derivative is the acceleration, how the rate is changing. So let's go ahead and see how we break this problem down. We start with the line, a car is traveling 65 miles per hour when the brakes are applied. Since it's traveling, that's how I knew this was the velocity. Miles per hour is a rate. So I have the velocity, the derivative of the original function, the position or the speed. Now, it says when we hit the brakes, so our time is 0. This is the exact moment our clock starts ticking. And we know that it was going 65 miles per hour from the question. So our speed at moment 0 is 65 miles per hour. Now here's the problem. The other piece of information, the deceleration piece, it's given to us in feet per second, not miles per hour. So we need to convert to the lowest common value, let's say. So I need to convert 65 miles per hour to feet per second. So I'm going to take my 65. Miles per hour means miles per hour. But I don't want miles, so I need a miles that's in the numerator to cancel with a miles in the denominator. I know that there are 5,280 feet per mile, and so I can cancel these out. But now I still have feet, which is what I want, per hour. That does me no good. I need this hour in the denominator to cancel with an hour in a numerator, and I want to end up with seconds in the denominator. So if I look at what do I know about hours per second, well, I know that 1 hour has 60 minutes, and 60 minutes has 60, each minute has 60 seconds. So 60 times 60, there are 3,600 seconds in 1 hour. I can now cancel this hour with this hour. So I'm left with my 65, my 5280, and well, the 1, but I don't need to write that. I'm left with feet in my numerator, an invisible 1 in the denominator I don't need, another 1 in the denominator I don't need, but 3,600 in the denominator with seconds. So when I go ahead and simplify this math, and since it's a fraction that doesn't end, I'm going to keep it in its most simplified fraction form instead of saying 0.3333. I now have feet per second, not per square second, but that's because, remember, I'm talking about velocity. I'm just changing 65 miles per hour into 286 thirds feet per second. Now we're going to get into feet per square second. The deceleration has a specific value. Now, even though up above we said the second derivative is acceleration, deceleration is just acceleration with a negative value. So acceleration is the derivative of velocity. So I can take its antiderivative to get back here, where negative 22 would be my answer. So let's put this together. Step 3. I know the if we knew v prime, then we could integrate to find v. I know what v equals in a specific case, but I don't know what v is by itself. Well, in the previous statement, we said v prime is 22. Well, I can find v if I have v prime. I'm just going to take the antiderivative, which since I only have a constant here, rule 3 said when you have a constant, you just put the variable with that amount, and then we always add our plus c. So I had the deceleration. I took the antiderivative to get down to velocity. And now that I have velocity, I can take the antiderivative to get down to my original function, which is the speed. So I'm going to take this velocity formula, and I'm going to take the antiderivative of that. I'm going to take what was 22t to the 1. I'm going to add 1 to the exponent, and then write the reciprocal of that. I need to integrate my constant c by putting my variable with it, and then I need another plus c, but we've already used c, so we're using the d. This is similar to the previous problems. So I can simplify this to be positive 1/2 times my 22t squared, and I can go ahead and simplify this even further to negative 11. So I have my original function. I have my velocity function, and I have my acceleration function, but really at a specific time. Okay, I've got something I can now solve for C and D, so I can use it to find how far my car traveled. It says when the car stops, well, when the car stops, it's not moving. Its speed or its position is 0. So that means this particular function, when you plug 0 in, will equal 0. So I'm going to put 0 in for my variables. I'm going to set it equal to 0. And the 0 causes everything to drop out except for D, which is 0. So it turns out I actually didn't even need that. Now, we also have one other piece of information. We said the velocity at the beginning of this time, which we converted from 65 miles per hour to 286/3 feet per square second. So I'm going to go ahead and I'm going to take this velocity function and say, hey, when you plug 0 in, we know it needs to equal that. Well, the 0 is going to tell us, therefore, that C is equal to this. Be careful, your actual problem could say, 5 minutes later or 5 seconds later, so this would not be a 0, and we'd have to do more math to solve for C. Okay, I've got all the pieces. I know what D is. I know what C is. So I can come back to that function and work with it in a minute, but I did need one more piece. It said find the time to stop. Well, that's when the velocity equals 0. So I need to go back to the velocity piece where we had solved for C, and I'm going to plug in that formula with, where did I go? Hold on, I'm down here. So we know that this for time t, I don't know how long it's traveled, right? So we've used the 0 to know the output, but what if we don't know the time, but we do know the rate? It has stopped moving. So I can solve for how long the car applied the brakes for by using a generic t. So I've subtracted the 286/3 over, I've divided by 22 and done the math, and the car traveled for 143/33 seconds. So I'm going to take my speed function, the position of the car, and when it's braking for this long, doing the math, the car traveled 206.56 feet. That was a lot. You might need to rewatch that one to hear it all over again.